We'll start in about 1 minute. We see a lot of people joining the seminar now, just making sure, give enough time for everybody to join in case of any technical issues.
And just, this is John, just double checking you can hear me okay?
Hi, John. Yes, we can hear you great.
Okay, great.
Before we have Chad Cusco introduce, I just want to make a note to everyone that we will hold questions to the end of the seminar. And if you have questions, you could type them either in the chat or wait to the end and you could ask through the, you could unmute yourself or raise your hand and we will unmute you, or you can unmute yourself. So at this time, Chad, I can ask you to do the introduction and we could begin.
Sure, thank you. John, we appreciate taking the time today. My name is Chad Cusco. I'm the operations manager of the NERI Lehigh experimental facility. We want to thank everybody for joining us today for the seminar entitled Design and Retrofit Methodologies for Buildings, Full Building Experimental Validation for Performance and Urban Resilience by Professor John Vanderlint, Colorado State University. Dr. Vanderlint is the George T. Abel Distinguished Professor in Infrastructure in the Department of Civil and Environmental Engineering at Colorado State University. Over the last 2 decades, his research program has sought to improve the built environment by making structures and structural systems perform to the level expected by their occupants, government, and public. He has served as a PI on a number of NSF projects, utilizing a number of NEAS and NERI shared use facilities. John, I'll turn it over to you. Thanks again for your time.
Okay, well, thank you very much. Let me share my screen here. Okay, great. Well, thank you, and thanks to NERI Lehigh site as well as NSF and of course Design Safe CI for hosting this event. I'm trying to frame with this. These are 2 large multi-university NSF sponsored projects that span from about 2005 to about 2014. So they span, almost a decade, and there were 5 universities on one and 7 on the others, and I'll get to that shortly. As many of you know, urban or community or even regional resilience is kind of at the forefront of much of the research, much of that being sponsored by NSF with interdependency research, things like that. But one of the important things that I wanted to get across is that, and of course that was in the abstract, while buildings are not sufficient, building resilience by itself is not sufficient for community or urban resilience. It is necessary. It is something that has to be there. So that brings me to, many of you have heard of Maslow's hierarchy of needs, and that's looking at things like shelter at the very bottom, and that's really our current design approaches. That's things force-based design, things that the most basic formulations in ASCE 7 and things like that. But as we move to looking at resilience, we start looking at other things such as the property itself, the social stability that results from the building being intact, and things like that. So currently, strength-based design in the U.S., and I saw the list of some familiar names, and so many of you know this, but currently we, a lot of jurisdictions use IBC. National Design Specification for wood is referenced in there, and then IBC loads come from ASCE 7. But the key is to remember that these are the minimum design loads for buildings and other structures. So currently we look at seismic forces at the system level when we go through, but then we break it down to the sub-assembly level to design. And so what happens is that the actual performance at the system level is really we're not guaranteed a certain level of performance. And what we see is not just in earthquake engineering, but with all natural hazards, what we see is that we get these rare events. And even though you look at the dates on the right and they don't seem that rare, but but these rare events that dictate changes or permutations in design philosophy, and they change our way of thinking, and that's what's going on right now. And so in earthquakes, why do a system level validation? Well, in earthquakes, and particularly in wood, the sum of the parts does not equal, I said does not always equal the whole, but it almost never does. And so we look at this, we design these components and these sub-assemblies, but it's very difficult to model the boundary conditions. And we see this particularly in light frame and even other types of wood, simply because it's difficult to enforce all those in space and time. And so this system level testing provides us that verification of the models and even a validation of a design approach. So that brings me to the capstone tests in Miki, Japan. Miki is located about 40, 45 kilometers from the city of Kobe. Kobe was badly damaged in the 1995 Kobe earthquake, as the name implies. So there were two major objectives back in Nicewood. This was to confirm that a representative mid-rise wood frame structure designed using a performance-based seismic design approach, and that approach was developed during the middle 2 years of this 4 to 4.5 year NSF-sponsored project, and then we used that to design this building to demonstrate that the performance at full scale was what we had intended. But then there was also this kind of key underlying objective, and that was to provide a general understanding of how mid-rise structures behave. Granted, this was designed with performance-based approach rather than a typical equivalent lateral force procedure, but it did give many of the practitioners involved in the project and around the country and world a feel for what a 6-story building can do. So this is E-Defense. Some of you have probably been there. That building on the right is actually a specimen preparation building. The weather can get pretty cold there in the winter, and so that's a 6-story building with I believe a three-story door. When this facility was built and finished up, I believe in about 2004, when this was constructed, they didn't really envision probably testing 5, 6, well, at least 6 or 7-story buildings, and so. So here, this, if you can see my cursor right here, is the specimen preparation building. And then this is a 10-story building, and this house is the shake table, and this door is about 6 stories tall. This is the shake table. It's 50 by 65 feet or 15 by 20 meters. And again, this is, the facility is quite large. You can see it going up 10 stories. So each section you see here of the door is a story. The payload, the capacity is around, I believe, 2.5 million pounds. So you can put a 2.5 million pound building on there and get good performance, at least tuned performance. So this is our wood that's been shipped. This combined with the steel, 20 shipping containers out of the ports of Vancouver, Seattle, and Los Angeles. Back then and now for that matter, we shipped U.S. products and actually Canadian products, which are used in the U.S. quite a bit. And that was primarily to ensure that the wood types, everything was similar for U.S. construction. And here we can see we did use 2 crews of Japanese carpenters, I think 2 crews of 4 or 5. And here you can see the first floor going in and then a steel moment frame down at the base, but it can lock down, as I'll explain in just a minute. And let me jump back. You can see this is the shake table. So there's always testing going on. And so this is this was, I believe, a 5-story steel building. They were looking at non-structural as well as structural effects. And so on test days, we would, of course, not be doing our construction there, obviously. This is the first story going up. And this is our queue of lumber that's being cut to length and prepped. This is actually the first story, and you can see the 3x6 sill plate. Everything was 2x6s, but you can see this actually looks more like cross-laminated timber. So we've got so many. I think this is what 15 or 16 on some of the stud packs, and then this is the continuous rod hold down that you'll see go up all the way to the roof, and it bears on each story, and that's just typically used in anything of 4 or more more stories in high seismic zones. And then we're getting up to the top here. I think we're about 5 stories up, still going. And here we see a view from about 5 stories. And this is a human kind of perception tuning experiment going on here. If you're wondering why somebody's sitting in the middle of the shake table, it was actually some very slow tests. So the test program itself, it consisted of 3 days of testing. Each day of testing there is quite expensive, just simply to charge the accumulators and things like that. And so, you know, and it's that way with all these sites, all the NARI sites, all the former NEES sites, you know, testing a day of test. So you make the most of your as efficient as possible and make the most of your test days. And so what we did is we tested basically on these 3 days, June 30th, July 6th, and July 14th. This first test was a steel special moment frame combined with wood. So it was one story steel, 6 stories wood. And it was tested to, now this is about a 50% in 50-year and a 10% in 50-year event. And that was primarily because it was the focus of the project was wood, so we didn't want too much damage. And so then we came down to a week later, July 6th. We locked down the steel moment frame and then tested same earthquakes, tested just the 6-story wood structure, performed very well. And then on July 14th, we had a big media day with about 600 participants and press and all sorts. And so those are the shakes that I'll show you because, of course, nobody wants to see the small shake. So we used 180% of the Northridge Canoga Park record. And what many people don't know, Takatori is a very severe motion, but it's severe in displacement. That's a recording from the Kobe earthquake that you see in red. But the spectral acceleration itself is actually far exceeded by the Canoga Park record if we scale to MCE. And so that's what we did. And so here is the long direction. This is the 2,500 year shake, or what we in the US refer to as MCE. And hopefully you hear a little audio. You'll hear them count down. So I'll talk and then I'll be quiet when it shakes so you can hear any cracking. And this was, so the building takes up the full shake table. I think we had 1 meter on each side. So we're about 14 by 19 meter, sorry, about 13 by 18 meters. Here we go. And it is a triaxial shake table. So that's, when you have wood with a lot of openings, it's important to be able to investigate that, although not always critical. That all the cheering here was probably just me cheering. So this is the 7th floor, or essentially the 6-story wood. This is a corner. Good Morning America had said if we could put some furniture in, that they would show it the next morning in the U.S. And do a short story on it. So we agreed and ran out to the Japanese used furniture store. And here you can see what happened here. So picture yourself having a nice quiet breakfast there, reading the paper. And again, they'll count down. That's to check the instrumentation and that it's recording. That's why it takes so long. And then they'll count down again in the control room right after. And so this, so you can see, now again, you don't see a lot of drywall damage though. You just see, you of course, 6 stories up in a building with a period of about a half second, you're on the plateau region. So you're certainly going to see some accelerations. So this is from a mathematical or an engineering perspective, this is what we saw. So this is seismic test 1, 2, and 3. So this is our smaller shake design level or design basis. And then this is our MCE shake. And so you can see this is in millimeters, but we're seeing about 1,825 kilonewtons. So on the order of, let's see, I guess I'd be on the order of about 425 kips. And and then 211 meters, or about 9 inches at roof level of displacement. This gives you an idea of, we did have some accidental torsion. We didn't actually expect this much. We expected a little bit, but with a triaxial motion that can be induced just because, again, it's that enforcement of time and space that I talked about. If we think of all peaks occurring at the same time, like a first mode, you're not going to see it. But here you can see that we definitely have some torsional issues. It's exaggerated, obviously, for you to see, but it was there. And then, interestingly, the largest interstory drift occurred right here. That room that you saw was this room shaking, and the largest drift occurred here. Sorry, it was actually this room. Excuse me. So this was the room that you saw with the small kitchen table, and this was about 3.1% drift. So the performance expectations. Now, the first test was led by a co-PI on the project, Andre Filiatro, and this was a 2-story building that was tested at Buffalo. I wasn't going through that in the interest of time today, but this performance expectation table that you see here was developed from that 2-story test at Buffalo, and that was a 2-story, 1,800 square foot townhouse with an integrated 2-car garage. And at a level, what we call a level C for performance expectation, you would see this type of damage at 2 to 4% drift, splitting of sill plates, cracking of studs, separation of gypsum wallboard from the ceiling, perhaps, and then buckling of gypsum wallboard or drywall at the openings. So interestingly, if you look, this is seismic test 2. So this was the 7-story steel moment frame, and then we got no damage in the first 2 shakes. And that's common for wood. It just kind of climbs the backbone even as it reverses. And so you really won't get a lot of damage as you scale up your tests until you get something that exceeds that. So then we did our seismic test 3 and 4, which were the same level as the 1 and 2, but with the wood only, and that's why you don't see damage. But then we got a little bit more propagation of the cracking. And this is just one example to show you. This is the second floor. So what was perhaps most interesting, and this, it was anticipated, but I wouldn't say it was expected, is that if you think we had the 3.1% drift as a maximum, we had quite a few of the levels and the walls and the stories going to 2%, some going to between 2 and 3, and then the maximum at 3.1%. But really our damage was actually more like this. We didn't even see much crushing of corners of the gypsum, and so it was really a level A. And so what we expect from a mid-rise building, one of the major conclusions is that the damage levels, it's very different than what we expect from a low-rise building. And so one of the reasons for that, the major reason, is that the shear wall stacks themselves, this is a stacked shear wall design, these 6-story shear wall stacks, 5 and 6-story shear wall stacks, they actually bend, and they actually almost act as tension and compression members as you get this global response. And so what you see here is, you see at the mid-rise level, is you see a good portion of that deformation is actually coming from not from the shear, as we expected some of that. We do model that, but in general it was pretty dramatic. We expected maybe a shift of 1 performance expectation level, not 2. So I want to jump to the next major project. So Nees Wood looked at developing a performance-based seismic design philosophy, in this case for mid-rise wood frame construction. So Nees Soft began in about 2010, about 2010, and the full title was Seismic Risk Reduction for Soft Story Wood Frame Buildings. Again, sponsored by NSF, and for this one, we were using a number of different labs. We did some smaller, leveraged with other funding, doing some other smaller lab testing and in support of this, as well as the major NSF portion. And this started basically in that buildings built prior to the 1970s don't meet current code. Not all of them, but a lot of them. And so there was a CAPS community action plan for seismic safety in the Bay Area in San Francisco. And they said that if there was a magnitude 7.2 earthquake on the Hayward Fault, now granted that's very large, but 43 to 80% of the multi-story wood frame buildings would be deemed unsafe. And so the issue was people wouldn't be able to remain in those buildings. And the fear was that they would leave the city, and then the city of San Francisco or much of the Bay Area would lose its character and really in a way that's a resilience concept. That's population dislocation or out-migration from an area. And in addition, 25% of the buildings would collapse. And so of course that's a fatality or a casualty issue. So then came about the ATC 71-1 project, and that resulted in a document called FEMA P807, which was a procedure. It was really almost like not really a neural network, but it was more like just a large database lookup procedure. They analyzed 100,000 or 200,000 different configurations of these soft story wood frame buildings. And the key is when we say 43 to 80% here, when they say that, there's thousands of these. I think the first estimate was 3,500 of these alone, and then and that's gone up since. And these buildings, they're not small buildings. They're 10 to 20,000 square feet with, 2-story apartments threaded throughout. So each one can have, 60, or about 20 to 30 units with many people. So NESOFT, in support of that, we looked to this was a 5-university industry funded project. And the idea, we had a couple of major objectives. It was to try and experimentally validate P807 from a practitioner standpoint. In other words, did that method work, but also to look at performance-based retrofit methods. And then also to be looking at, of course, being able to try and model collapse better, because as I mentioned, and so this further underscored the need for system level or full scale building testing. So I won't go through this in too much detail because I'm going to focus on the shake table test, but we did look at some assembly testing, and this was the leverage testing from various smaller sources. And then 2 major full-scale building tests. One was the 3-story slow hybrid test at NES at Buffalo. So that didn't use the shake table facility like the test that Andre Filiatro had led back in 2006. In fact, it was a 2-story structure, and then the first story was going to be retrofitted, but the retrofits were numerical. So all of these retrofits that you see here were actually done numerically at the first story. And then the boundary conditions enforced with the large long stroke actuators at Buffalo. And then the 4-story shake table test at NES at San Diego, which will be the focus of the rest of the presentation here, or at least a portion of it. And for that, we looked at a number of different retrofits, which I'll get into, and then pulled all the retrofits out to study the collapse of the building. So this is the crew. It's an outdoor shake table. That's why everyone is looking so tan, regardless of how much sunblock you put on. But here we see the 5 PIs. Here we have our collaborators from Simpson Strong-Tie who worked on 2 of the major retrofits with us and donated that product. And then our 2 PhD students right here, and then 5 REUs that participated. And I believe actually we're actually thrilled that I believe 4 of them went on to graduate school for masters, mostly in California, but they're in there, probably completed now. And then a soft story building, and this is I may be with all the structural engineers I saw coming on with the familiar names. This is perhaps preaching to the choir a little, but soft story building is a building with low lateral stiffness compared to these upper stories. And here you can see the size of these buildings. They're not, not like a single family dwelling. And so we did some data reconnaissance, went out, they have them in New Zealand as well. Not too many collapsed in New Zealand, but they did have a lot of damage to some of them. And there's actually a car under here. And in New Zealand. And when I spoke with somebody, I think it was the owner of the building, he said that the person, there was nobody in the car, but they had actually gone upstairs. They forgot something, went upstairs to get it, and then the earthquake occurred and collapsed and crushed their car. So, okay, so the life cycle of this this 4-story test building. So we started with construction. We did a lot of prefabrication off-site, which you'll see in a second. Then it's ready for testing. It's shaking not in the direction of the towers. The towers are actually to protect us sitting in the control room. And then we did first retrofit was cross-laminated timber rocking walls, and that used the FEMA P807 method, and then a steel special moment frame, and that also used the FEMA P807 approach. Then we steel special moment frame with structural panels, and that was a performance-based seismic retrofit approach. And I should mention, I should have mentioned this, but the approach built on the direct displacement design that was originally developed for reinforced concrete by Priestley, and then in Neeswood, and then this retrofit procedure built on that. But one of the big major contributions that I won't talk about in detail today, because it's a very detailed formulation, but would be happy to send the paper if somebody wants to email me. And that is that this actually we brought torsion into that, because direct displacement design in general was not able to account for torsion. And so, but with these soft story buildings with the open fronts, there's a significant amount of torsion. And then a viscous damping device plus wood structural panels, and that was a performance-based seismic retrofit. And then we did the collapse testing, and as you can see from the small image on the left, it was successful, if you can call it that. And then recycling and disposal as much as possible. So this is the 4-story test building that you see here. And again, this we tried to make it as similar as possible, but we can't always do that. And so, for example, we had our wood siding. We didn't include trim. We felt like that wouldn't do anything. Stucco, it's not on all buildings. Sometimes it's on one side. It just depends. So we opted not to include it because it would have been difficult to repair and then dry. And but we did include things that we felt, the plank flooring, the hardwood floors. We used gypsum wallboard instead of plaster on lath. And so there were, but we did have all the seismic weight in there that you'll see. And so the prefabrication, this was to, as I mentioned, the time on these shake tables is very expensive, and it's very in demand at all these sites. And so, it's critical to do as much as you can in preparation. So we were there for about 2 weeks, and you can see with the professional contractors working on even prefabbed the floor system, as you can see, which is a little unusual, but if you have enough crane power, you can do that. And then this is the graduate student. He's working at MKA now, Pori Bomani up in Seattle, and this was his dissertation. Leading up to this project, leading up to this test. Here you can see this is one of the things that you have to do for testing on a shake table is you have to have the interface so that you can connect where you want to connect depending on what the structure type is. And so here we'll see the building going up. And I should add that if you see these little braces here that were put in, those will of course be taken out, but the construction crew themselves that was used to building typical, Southern California wood frame construction, they actually, the building with that open front, it made them so nervous that they asked if they could go ahead and brace things just while they were building it. Now, of course, it didn't have all the siding on it, but that gives you an idea of how soft these buildings are, and weak for that matter. So a closer look inside the building. So there's that transfer plates that I mentioned, and then our anchor bolts. No hold downs in this case, except when we retrofitted. Hardwood flooring, and one of the reasons for the hardwood flooring, this is actually the cheapest hardwood flooring you can find, but it was necessary because much of the strength, there's no hardware in these buildings. These are 1940s style buildings, and so So much of the strength comes from these non-structural components. It's a big portion of that. Here's one of the RUs, probably repairing drywall actually here, or maybe installing it. I can't remember on that photo. And then so here we see our 2x10 Douglas fir DFL joists at 16 inches on center, and then our 1x6 plank floorboards, and then the 3/4 inch hardwood flooring. And so that was throughout. And so if you take a look at this, it looks like somebody forgot the hardware, all the WSB or the Simpson or whatever products. And but in fact, these buildings, everything's toe nailed, everything's built like this. And so this is essentially, except for the sheathing, nearing completion. So if we compare it to some of the buildings that we saw when we did our walking tour of San Francisco and the Marina District to try and assess some of these buildings, that was about a few years out from the project. That was for the proposal, actually. Here you can see that we tried to reproduce this, but at the scale that we can on a shake table. And the shake table here is 25 by 40 feet. I didn't mention that. And so our building is actually 25 by 40 feet. So the first retrofit was the cross-laminated timber rocking walls, the FEMA P807 method. So that involved making sure we got the shear transfer through the diaphragm. So you're looking up at the underside of the first story, and you can see that we've now sheathed the underside of the floor to try and stiffen that up. This is the weak story tool that right here, sorry, that comes with, if you can download that from the FEMA P807 website, and this is the document. And this was actually finished up in about 2012, and we tested in 2013, and then we actually caught bugs and in this and communicated with David Moore and colleagues that developed this. And I think we were some of the first users outside of them probably to do this test. And then we had a component test, reverse cyclic. And so you can see we get our backbone, and then we can import that backbone directly into this. And again, what it's doing is it's doing based on the configuration and a certain set of rules. It's doing essentially a lookup to tell us what we need to do. These are the cross-laminated timber rocking walls. So you can see there's slotted holes to connect into the floor diaphragm. These were a little beefier than they needed to be, but they were available to us. And again, big tests, you cut costs where you can. They had no effect on the performance of the wall itself. And so here you can see we're going to shake in this direction. And here's our soft front. So here you can't see, but these are actually, but here we had 3 CLT panels in this direction, and then these 4 rocking CLT panels. They're about 2 by 8 feet to only 2 feet long, and they'll take the torsion out, at least we hope. And so for our response in the shake direction, we're getting about a peak of about 1.5%. This is Cape Mendocino Rio. This motion, I believe this one caused the largest response. We did a few different ones, but for this particular retrofit. And so you can see it right here, but a nice response really. I mean, it's still, building's still not, I mean, the building period is still quite long, as you can see from that response, but fairly consistent. And then in the transverse direction, you can see we were able to eliminate the torsion. Our peak was only 0.12 inches. So our takeaways on this one were simply that, we could get a peak response of about 1.5 inches only. It did isolate the first story, the response was primarily at the first story, so the upper 3 stories. So again, this may still be a soft story building by definition, but part of the logic was that for P807, in this case, at least for the city of San Francisco at the time we did this, they were looking at trying to retrofit only the bottom story to 50% of MCE. I think they may have changed that more recently, but really no danger of collapse and no significant structural damage. So I'm gonna skip 2. I'm gonna jump right to phase 3, which was our steel special moment frame plus wood structural panel. So that's our performance-based design. So here you can see this is typical down in the bottom right, typical moment steel special moment frame. Oh, sorry. Had a feeling that might happen. There we go. And we can see the two retrofit locations up here. So this is, and now keep in mind, so a car would drive through here, and then of course everything has to be positioned so doors can still be open and things, because the idea is to keep the garage intact. And in this case, it was a little bit beefier because we're doing the performance-based seismic design. And so for this one, we then went up into, so this is the second story, and of course, third and fourth look similar. And this is probably the largest in the building. This is a large intersecting shear wall. And so the idea was then to, if you look back on right here, we're going to bring those continuous rod hold downs into these weldable cages. So these are welded onto the top of the moment frame, the beam. And so we bring those down, so you can see we're drilling down. And so this is really, really rolling up your sleeves and getting in and doing this. And of course, much of this was done by all of the students, by some of the staff there, by me, others. And then when needed, we would bring in professional carpenters, but often that was just to, for example, to sheathe the underside of the things, sheathe the underside of the floor, or things like that. And drywalling, for that matter, the majority of the drywalling. So here you see the example. This is just a coupler nut right here, and then we and then we go into, and as this goes up, these will get smaller and smaller, and they're controlled by not just yield, but they're also controlled with an allowable elongation limit. So here's our installation, and this train, believe it or not, each of these takes about 1,000 pounds of shear, each of these wood screws. So this is transferring the shear from the building. The whole building's only about 120,000 pounds. So, and then we had a perfect pin at the base, just so that we could numerically model it well. But you can definitely do that. And so what we saw, peak response. What we saw was at roof level, we were getting about 4.5 inches. In yellow, you see inches, and then a fairly nice response. You can see DDD. Ideally, we'd want this to just continue out here perfectly, like you see right here in the light blue or whatever color that is. And we didn't see that at that top story, and that's common in all direct displacement design and even some of the other performance-based design, because to get that, there's so little weight on the roof that you would actually have to reduce the design to a level below current code, which we're not, no one's willing to do, of course, or nobody can do. So here's the shake. It's a fairly quick one, so don't look away. It's a little loud, sorry. But if you watch that, what you did see is you saw more than one mode, and that's because if you're really just getting a soft story, almost like an isolator mode in the P807 still, if you shake it hard enough. So there's still some danger there. But overall, it's certainly a lot better than what the biggest issue is that in performance based, in general, the people living in the building would likely have to vacate the building for a period of time, on the order of at least weeks, to be able to do that. Whereas with the 807, you can even you can bolt frames and you can do things because you're working in the garage, and so that was really the objective of that. And so here you can see on that third story that we were getting a pretty good drift, and that's what's really causing that second mode that you saw if you caught it. So the takeaways, about 2 inches, a little bit more maybe, but not only shear deformation. Again, we saw that the same thing up at the third story that we saw at the fifth story and the 6th story capstone test. Our models have trouble predicting this. I think we're getting better at it. One of the co-PIs, Wai-Cheng Pang at Clemson, has a very detailed model that's now able to do that and predict collapse. But it's really I like to think, of course, they've worked on a number of projects, but I like to think that these projects have helped with that modeling. But survived an MCE with no structural damage, just some drywall cracking. It was easily repairable, and it would likely survive a much more intense MCE. Okay, so I'll move to collapse testing. The first thing you do is you pull out all the expensive items. So that's 97% of the instrumentation. We did talk with San Diego and agreed to pay for a certain amount of instrumentation that would be sacrificial, as we call it, including cameras, and left about 3% plus some cameras. The collapse motion, we used Cape Mendocino, Rio, Loma Prieta, as well as Superstition Hills. And so if you look at this, Superstition Hills right here, so this is MCE. If you look at it, it looks like the period of the building is close to 1 second when it's not retrofitted. So they're all about the same. And, certainly in what we'd call that plateau region for the design spectral acceleration, you see, much higher values for Cape Mendocino and Loma Prieta. But one of the major things that we learned in collaborating for years with the Japanese and going over and watching their collapse tests on 2- and 3-story buildings was that, and of course those that study P delta know this, but it's not acceleration doesn't always, in general doesn't cause collapse. It's really displacements. It's like pulling the rug out from something. So if you take a look at the spectral displacements, and again, the Cape Mendocino, Superstition Hills, but then when we zoom back in, if we're at 1 second, they're all about the same. But then as the building gets damaged and the period elongates, you can see Superstition Hills takes off. And so what it's doing is it's really, really going to force the building to move. And again, this is evidenced down here in the ground displacement. Okay, so here is the collapse shake. So this is Superstition Hills at MCE level. And the student got a little overzealous, so the audio's on, but and he's up in a large lift about 80 feet in the air, or about 60 feet in the air, I think. And on the top, you can see some added seismic mass that was strapped down, and we had steel strapped in throughout this to bring it all up to design weight. So probably on the order of 40,000 pounds of added mass. Okay, so we then, this is Superstition Hills again, because remember, we're actually at about, I believe it's at about 16 or 17% drift here. So we've moved over about 16 inches, maybe 17 if memory serves. And it's still, nothing's holding it up except itself right now. There's nothing in there. It's not bearing on anything. I do want you to pay attention. There's a camera right here. In this room that you see in here was furnished with some cheap thrift shop furniture, just for illustration. But unfortunately, you'll see we didn't get a good shot of that. So here's the shake again. And keep in mind that those towers saved our lives because the control room's right behind that right tower. So this is that camera that I pointed out. So and you can see all the people watching here, and they're in a few different locations. And then you can't really see it, unfortunately, because it was a 10 a.m. test. It was a morning media event, and to try and get them the footage for the evening, the 5 o'clock news, I guess, is what they requested. And so, so unfortunately, you won't be able to see that. But this is that camera that I pointed out that was on the safety tower. And then here, and so this is the room that you saw there, and then the camera, of course, gone in this case, and some furniture from that building. And so what we saw is so the modeling procedures actually modeled the collapse quite well. It's never perfect, but we were able to get within about 10 to 20% of the expected displacement at collapse, which is with wood is quite difficult. And just a few images. And then demolish and recycle, disposal. And so, you can see a huge displacement before collapse. We're looking really at about 25, sorry. I shouldn't use the mouse, that's my problem. About 25 inches on these. We did a small shake just in between those. That's why it says Superstition Hills test 6 and 8, but it didn't do anything. We wanted to, we knew we could collapse it with another MCE. We wanted to try something very small, kind of from an aftershock scenario. So this brings me to, as I kind of alluded to or promised, I guess you could say at the beginning, is tying into urban or community resilience. And so that buildings are a necessary component of the community, as we know. But it's the ability of a community to prepare for and adapt to changing conditions and to withstand and recover from disruptions to its physical and its non-physical infrastructure. And so the community can think of that as, for San Francisco, it was the whole city. In other words, that's where they're able to pass their governance. That's where they can pass laws or ordinances. So they now have a mandatory soft story retrofit ordinance for those 3,500 or 4,500 buildings. And that's that collective sense of decision making. But then looking at changing conditions and disruptions, so looking at any hazard, in this case earthquakes, and it's really these changing conditions, and of course in the case of an earthquake, it's a very sudden one. But then looking at the physical infrastructure, and as I mentioned, buildings being key to that, and then integrating them. Now, with one of the key issues is that building codes currently look at single structures or a single component within the urban landscape or within the community. And so one of the keys will be, and moving forward, will be you can design a building for a certain level of performance, but it still doesn't guarantee that people can stay in that building and that it's operational. And then non-physical, and this involves sociology as well as economics. But the key really is survival, the safety, the availability of things, and then safety and security. And so again, that brings us back, perhaps moving from the very bottom, beginning to move up into the orange, and perhaps above that as we move structural design even from just performance or just force-based to resilience concepts. And so that leads me to a project that's led by Shileng Pei at Colorado School of Mines, which is to develop and validate, it's a NARI Tallwood, it's to develop and validate a resilience-based seismic design philosophy for tall cross-laminated timber buildings. Cross-laminated timber, you could think of it as almost for those of you not familiar with it, you could think of it as almost like a plywood on steroids. It's been referred to, in that it's 1.5 inch thick plies, and so you do layups basically, and then of 2x6 or 2x8, and then you lay the next layup, or the next layup goes orthogonal to that, and it gets glued together. So there was a planning project. This was from 2013 to 2015. That was also led by Shileng Pei, and this involved consensus building through a workshop, as well as discussion at the Forest Products Lab's Mass Timber Research Workshop that they hosted in 2015. And the result of that collaboration with a number of people that you see on the right was the NARI Tallwood project that started in 2016 and is ongoing. So to give you an idea of what that project involves, it's looking at defining tallwood archetypes. These have been defined to this point already now with architects, as well as then investigative testing at essentially at the system level and at the component level. So here you can see some assembly level testing that will occur at Lehigh, and it's I believe the setup is ongoing there, and then the two-story test at NARI at UC San Diego, and that was in a way a test of opportunity that the Shake Table was available, and so additional funds were raised to leverage the NSF funds from all the industry partners and other sources to be able to test that. And so these are rocking walls that you see here, two-story rocking walls in this case. But again, something like this has to be validated at least at full scale. And so what you see here on the right is the full-scale 10-story validation test. Now, this isn't necessarily this isn't necessarily the architecture of this. It may look more like one of these combined with one of those, but the idea of this would be then to focus on the non-structural. We'll look at individual and couple walls. We'll look at unsymmetric design and torsion. Even though it's a uniaxial table, we'll be able to do that similar to what you saw when the knee soft building collapsed a few minutes ago on the video. And so we'll be so right now we're in the I guess the midst, if you will. In fact, we just had a meeting a few weeks ago in Portland, and we'll be meeting at the Structures Congress coming up in Fort Worth next week to discuss some of this. And so we've, as I mentioned, the wood archetypes have been decided. We'll be at the San Diego Shake Table test, and now we're bringing in much of the design experience from some of the recent mass timber projects that are ongoing. Some of those are not in high seismic zones, and so that was really some of the impetus for this project. And then this was a component test at Washington State University as part of that planning project. And so here we see then just finally the configuration is dictated by research objectives in this case, and as everything is, and then ultimately design or resilience objectives. And so this building, and you can, I'd encourage you to look at on the Colorado School of Mines website if you want to see more. And of course, there'll be presentations over the next year or two at the various earthquake conferences around the world, but by Lang and myself and others. And this is but this went through about, I think, 27 major earthquakes with no structural damage and actually very little other damage, because as this rocks, it's only transferring shear, but it's not transferring any of the uplift into the diaphragm and the rest of the structure. So it's, just amazing to watch this in action. And so with that, I'd like to wrap up, and thanks very much for your attention. And this work was funded by through CMMI, through the National Science Foundation for both the major projects. And then we had a lot of other contributions, always trying to leverage that as much as possible. And there's way too many people to name that were part of this and part of the project team and others. And again, just for the two projects, the two large levels of acknowledgement. Thank you.
Thank you, John. So at this point, if anyone has any questions, you could either unmute yourself and just introduce yourself and ask your question, or if you do not have a microphone access, you could type your question into the chat and I will read it. So we'll give a few minutes for questions and we can begin. And if you want to ask a question, you have any difficulties, you could use the participant panel to raise hand, and I could try to unmute you if you're having any problems. Okay, John. Well, it looks like everyone is blown away. No questions. No questions are coming up from the panel, but or for the participants. So I will ask Chad just to do a final wrap up, and thank you for your time.
All right. Thanks, everybody. Thank you.
Thanks again for your time. For anyone interested, we're going to continue the NERI Lehigh seminar series. Wednesday, May 9th, Professor Monique Head from Morgan State University is going to present at 12 o'clock noon Eastern Time, a presentation entitled Investigation of an AFRP Reinforced Column with Energy Dissipators Under Cyclic Loading. That'll be posted on the Design Safe website soon with an announcement regarding this going out, where you can also register online for this. So again, a big thank you to John for the presentation today. And if Monique's topic interests you, please look forward to registering to that. Everyone else, have a great weekend. Thank you again for participating. Bye-bye.
And I also want to note that we will archive, with permission from John, the presentation on the Design Safe website. And that is a video, not a presentation file itself, if he's okay with that.
Yeah, absolutely.
Okay, great. Thank you.
Okay. Thank you, everybody. Have a good weekend.
Thank you. Bye-bye.
Bye.
Bye-bye.